Welcome to a lesson with Dr. Powell. Let's take a look at how we can approximate the value of a function. Suppose we want to approximate, let's say 2.1, and maybe let's do 0.9. And we're going to this is going to be approximately, or it's going to be close to, it should be close to f of 2 comma 1 if the function is continuous and smooth enough, kind of connected in enough ways, kind of looks nice. So the way we're going to do this is we're going to look at the definition of the function. Suppose that we have 3x y squared plus, and let's do plus xy, something like that. Okay, so to compute this, first of all, we're going to see, well, let's plug in this 0.21, which is easy to plug in, 2, 1, so 2 for x and 1 for y. We end up getting 6 plus 2, so 8 is equal to 8. Now, to get this approximation, what we're going to do is we're going to say it's 8, but then we're going to add something. We're going to add the rise, or the rise of the tangent plane. What's the rise of the tangent plane when the xy coordinates move from 2, 1 to 2.1 comma 0.9? So there's a run. What's the run? The run is a vector, kind of you just subtract these two if you want. So, or, you know, what 2 to 2.1 is just 0.1. And the run from 1 to 0.9, that's negative 0.1. Okay, so that's my run. And so to get the rise, we want the rise of the tangent plane. So the derivative gives us a function which allows us to move from run to rise of the tangent plane. So we got to compute that derivative. All right, the derivative is a matrix, and we could think of this. We take we think that we have one output, so one row, and we have two inputs, x and y, so we have two columns. Now here, this is going to be the derivative of the output with respect to this particular input in this column. So let's suppose this is x and y are represented here. So the derivative of f with respect to x only, where y is a constant, that would be just 3y squared plus y, right? Because y is a constant, and so it's just x is the only variable. So this is like 3y squared is a coefficient there, y is a coefficient here. So you're just adding those coefficients of x together. And that's the slope in that direction. And the slope of y, in the direction y of the function, you think of x as constant. So that you take this 2, pull it down with the power rule, you get 6xy. X is constant, and then over here you would just simply get x plus x. So this right here is the derivative. Okay, now what we'll do is we'll see what this derivative is at the point 2, 1. All right, so we just plug in 2, 1. So plugging in 1, we get 4 in that component, and then over here we have 2 1s, so that would be 12. Plus 2 would be 14. So 414 is the derivative. And what we do now is we plug in what the run is to see what the rise would be of the tangent plane. And using a dot product or a matrix multiplication, we arrive at 4 times 0.1 plus 14 times negative 0.1. So we get 0.4 minus 1.4. So we arrive at just -1. So it looks like the rise of the tangent plane as a whole -1 as we move from here to here. So really we put it a -1 there. So in a good approximation of this, assuming that the surface is flat nearby, and a better approximation is just to go along, instead of just saying 8, is actually to go along the tangent plane itself and see what's happening. And we notice that the tangent plane actually drops a whole -1 as our run is this. So that means a good approximation for this would be 7 for the function. Thanks for watching.